So let's start with the last talk of the workshop. So we're very happy to have Hariharan from TIFR. Hari works on several different areas, including learning, optimization, sampling, and combinatorics, and also random matrix series. So today he'll be talking about the spectrum of the sum of two random matrices and various properties of that.
Thank you very much for the invitation to speak here. And I've learned a lot from this conference. I'm really happy to be here. Yeah, so I'm going to talk about joint work with Alok Gangopadhyay. This is on the randomized horn problem and the surface tension of Hives. We'll start with defining the randomized horn problem. So we'll say that lambda plus mu goes to nu if there exist Hermitian matrices A, B with eigenvalues lambda and mu respectively, such that A plus B has eigenvalues nu. So note that this is a relation because it's not a equality, because if you have two Hermitian matrices with eigenvalues lambda and mu, their sum could have many possible spectra. Okay. So Weil asked the question of determining necessary and sufficient conditions on lambda, mu, and nu belonging to the spectral cone, which for me will be the set of all non-increasing sequences of n real numbers for the relation 1 to hold. Lambda, mu are vectors. So as conjectured by Horn and proved by Klyachko, Knudsen, and Tau, the set of all possible nu given lambda and mu is a convex polytope, and it's a codimension 1 convex polytope because the trace equality has to hold. But beyond that, it's given recursively by some set of linear inequalities called the Horn inequalities. These are somewhat complicated to state, but I will give you an equivalent form of what these inequalities are. And in addition to having this polytope of all possible eigenvalues, there is also a measure, natural measure on this polytope, which is what you get when you add two random Hermitian matrices from the Haar measure. So given the spectrum lambda, you can take all conjugates of this diagonal matrix with eigenvalues lambda using random unitary matrices, and that defines the natural measure on the orbit. So if you take two matrices from this orbit independently chosen and add them, you get and take the spectrum, you get a probability distribution on this Horn lambda plus mu, and we'll be interested in this measure. We'll call this measure the Horn probability measure. Okay, so Knudsen and Tau, and more explicitly Kokurio and Zubair, gave an explicit formula for this Horn probability measure. It is this formula. It is the product of two Vandermonds. I'll get into this in greater detail, but two Vandermonds with parameters nu, lambda, mu, and this tau is this vector n-1 all the way to 1, followed by the volume of a certain Hive polytope that I will describe in detail later. Okay, so there is an explicit form for this measure in terms of this volumes of this Hive polytope, which I will have to describe to you. The support of the measure is the Horn polytope, which is defined by those inequalities, which I'll tell you now more detail. So to tell you what the support of the measure is, the support of the measure is actually can be given as a projection of a certain Hive polytope. So how do you get this Hive polytope? Okay, so a Hive is a function on the triangular lattice here, which satisfies all these rhombus inequalities, which say that this plus this has to be greater or equal to this plus this. In other words, if I take the function on the vertices of this triangle and take the piecewise linear extension to the interior of the triangle, I will get a surface, a polyhedral surface. That polyhedral surface has to be a concave surface. So this is what a Hive is. This polyhedral surface that you get has to be a concave surface sticking out of the plane of the screen. So such a thing is called a Hive. Now, if you put lambda and mu to be the derivatives of the concave function on this side and this side, then only certain mu's will be achievable as restrictions of such concave surfaces. And those mu's are precisely the possible Horn elements of Horn lambda plus mu. So this is actually giving a polytope n squared by two random variables, this Hive polytope, because there are all these rhombus inequalities. And that is a projection, that Horn lambda plus mu is a projection of this Hive polytope onto n dimensions, where those n dimensions come just from this last value. So you have this explicit description of the Horn polytope. And what is more, because of this expression of Kukrio and Zubair, you even have a nice measured theoretic expression for the Horn probability measure, which I will describe later. So here, for example, is an example of a hive. So this is, here lambda is 40, 30, 20, 10. And as you see, the slope here is 40, the slope here is 30, the slope here is 20, the slope here is 10. Then to follow mu, you go down again, slope 40, slope 30, slope 20, slope 10. By slope here, I just mean the second entry minus the first entry, because I'm thinking of this as a surface in the third dimension coming out of the screen. And mu here is 65, 55, 45, 35. This is 65 slope, 55 slope, 45 slope, 35 slope. You can check that the sum of the slopes entry here will, and plus the sum of the slopes here will add up to the sum of the slopes here, and that's the trace condition. And for these particular values inside, all the rhombus inequalities are satisfied. Namely, if you take any rhombus like this rhombus, you will find that 90 plus 140 is greater or equal to 100 plus 125. And this is true for every rhombus.
Sorry, this was a bit much for me. Can you just go over this picture?
This picture, yeah. Yeah. So, like I said, the hives are restrictions to the vertices here of a concave surface. Okay, so what does concavity mean in this context? When for each triangle you have a flat space, it says that if you take any rhombus like this plus this has to be greater or equal to this plus this. So that is what a hive is. So all these roughly 3n squared by 2 constraints define a hive.
And on the boundaries, you have this boundary constraint. So this lambda is a decreasing sequence, and you're adding up.
Yes. So if you want to, you can put the boundary constraint. Otherwise, you get a cone. If you're fixing lambda mu nu, then the hive polytope for lambda mu nu is this. And if the hive polytope is empty, that implies that such a triple does not belong to the.
That is by design concave because it's decreasing, right? Similarly.
Yes.
Lambda plus come up with the same thing.
Yeah, that's the trace condition. If that is not true, you will certainly not be able to find a hive, because when you go from here to here, you will not get the same as when you go from here to here. And that's, of course, true because you can never have a triple which satisfies this condition if the traces don't work out. But even if the traces work out, it is not necessary that you will have such a triple. And the condition for having such a triple is precisely that you can extend it to the interior in this way. Okay. Yeah. So there are many inequalities that in Horn inequalities. Those I believe are some of the inequalities, and all of them. So this is a necessary and sufficient condition. So yeah, so those will be incorporated in this. Okay, so this is this statement of Mutsendao, Kukrio, and Zubair. It says that the probability of observing nu n when you add xn and yn, where xn and yn are independent Hermitians with spectrum lambda n and mu n, is given by this expression. This is the volume of that hive polytope. I described a polytope. This is the volume of that hive polytope. And these are some Vandermonde factors, Vns. So let's define a certain function based on sigma, which I will define in the next slide. This is a function for continuous hives. So now so far we were talking about discrete hives obtained from doing linear extension on the lattice points on this triangle. But you can also talk about a continuous hive, which is a surface which satisfies the rhombus inequalities for every rhombus that belongs to that triangle. So such a thing will be called a continuum hive. And for a continuum hive, you can define this functional. Yeah. 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 Yeah, it is a consequence, but I don't know if it's an immediate consequence to see it. It will somehow imply, that is for sure, but how, whether to speak. So what you're asking is if the slopes of all of these are positive. So in other words, this line is going upwards this way. Here it goes further upwards when you come down. Does it imply that when I cover it by a concave surface, all of these slopes also are positive? It implies, but I don't immediately see a proof. Yeah. Yeah, so there is this functional on continuous hives. And what we showed with Scott Sheffield was that this gives a large deviation principle for the spectrum of the sum of two random matrices. So if you take this xn plus yn and call it zn, the probability that this zn belongs in a certain ball around nu n is given by when you take the limit as n tends to infinity. So what am I saying here? I'm saying that if I'm saying that you take lambda to be a curve like this. This is not lambda actually. This is the cumulative sums of lambda. Let's call it integral lambda. If you take mu to be a curve like this, then the lambda n are defined by piecewise linear extensions. So by piecewise, yeah. So this I'll call lambda n of 1. The slope here will be lambda n of 2. This will be lambda n of n. This is a kind of discretization of lambda. So you start with some continuous curves, lambda and mu. And from that, you derive a limiting statement about the lambda n and the mu n. Namely that when you take with these lambda n and mu n a matrix, then the spectrum of the sum will belong in a certain neighborhood of mu n with this probability. What is that probability? It's the infimum over a certain ball in this continuous space. So now this is a continuous ball, this is a discrete ball, this BIN, this is BI. This is a continuous ball. I mean, what I mean is that BIN is basically, so if this is nu, this is integral nu, then BIN is basically all curves that lie within a epsilon neighborhood in L infinity. Okay, so that's some set of functionals. So if you want to know what's the limiting value of the probability of landing in this ball under nu n, when your lambda n tend to infinity in this particular way, the answer is you take this ball, which is a set of all yellow curves around the white curve, and you minimize this functional. Now I'll tell you what sigma is, because without... Yes, delta minus the left derivative. Yeah. So this is how lambda n is related to lambda. So this curve is integral lambda, cumulative integrals. And this is a discretization of it. Yeah, so I should tell you what sigma is. So in a hive, we will talk about slacks in different directions. So suppose you have a quadratic hive for the moment, for the sake of argument, then all the rhombi which are red in color have the same slack. By slack, I mean this plus this minus this minus this. All the red rhombi have the same slack. So this is going to be sort of the paradigmatic situation when you have a continuum hive, because locally at almost all points a concave function is twice differentiable at almost all points. So this so we will talk about these average slacks which are locally defined. Okay, and if I have now so the picture now is that you have this enormous hive, and locally for some reason around a particular point it looks like a quadratic. So because it looks like a quadratic, all the red rhombi in the previous picture correspond to the same slack roughly, or at least the average. There is a certain average slack, and that is what we are going to call S0, S1, S2, which is the vector S. So it turns out that these hives with periodic Hessians, they have a volume. So you take a huge hive, but you say that its Hessian is periodic with a certain large lattice size n. So then the set of all such periodic hives, which are also have the property that their average slacks in the different red, blue, green directions are S0, S1, and S2, they have a certain volume. And this is the limiting volume of that. So one can rephrase this periodic Hessian condition using a torus and semi-concave functions. I won't do that here, but just trust me, there is a way of writing this in a truly finite way, what I just said. And you get a polytope corresponding to the average slacks S0, S1, and S2. And sigma S is the negative log of the limit of n tends to infinity of the volume of these polytopes raised to 1 by n squared minus 1. So would you prefer that I gave also the description using tori? There is a description using tori, but I don't know if it will be very helpful. It's basically that when you have periodic Hessians, you can add a convex function to the whole thing and get a bounded function. And then that bounded function will be periodic. And then you can think of it as a function on a torus, a semi-concave function on a torus, which also has a volume. It's essentially some linear transformation.
Here, not right? Is like take a like triangle with n like height and n.
Yeah.
And it picks the slack vector everywhere to be S.
No, the average slack is S. But additionally, the Hessian has to be periodic. The Hessian of this thing, which is going to be some measure valued thing in general, but the Hessian of this piecewise linear function has to be periodic.
But it's a finite
within the interior. So there is
periodic, as in from if I go from hive to hive, it should be the
no. There is only one hive. Yeah, rhombus to rhombus.
Yeah. From rhombus to rhombus.
Yes, yes.
Or even triangle to triangle.
Even triangle to triangle. But it's a Hessian. So the Hessians don't see triangle slopes. They only see the gaps between the slopes of adjacent triangles. So it's really rhombus to rhombus, the slack.
So the slack is for each rhombus there is a slack. And there are like three directions with
yes.
And the periodicity
is of that slack.
Oh, so
yeah.
So all the
So there is a very large hive here, and there is this fundamental domain. And no, this is not one of the rhombuses are tiny. But if you take a rhombus here and then you view the slack of the corresponding rhombus here, corresponding rhombus here, corresponding rhombus here, they will all be the same.
In the domain.
In the domain.
But then if I move
here also. So here also. The same is true here also. I'm ignoring boundary effects. So if you want to do this rigorously, you have to do it on a torus. Then you don't have boundary effects.
And n is the size.
If n is the size of the fundamental domain.
So the size of the hive is going to be
enormous, going to infinity. Yeah. Yes.
Like, that is anyway. That's because
yes. Yes.
N is on the
yes.
And there.
Yes.
And P and is the volume
of the set of all such
on the
hive. Yes, on the fundamental. Yes. 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 So if you take the negative log, this is convex by the Brun-Minkowski inequality. And it turns out that it's symmetric in S0, S1, and S2. There's a kind of shear transformation one can do on this torus, which allows one to see that S0, S1, and S2 are symmetric. So basically, I can do this torus like this, but I can also cut it here and translate this triangle down. And then I get a torus with a rhombus like this, and that will give you a different permutation. So this can be shown to give that sigma is symmetric in S0, S1, S2. And this is a non-trivial result, was first conjectured by Slack-Tenko and Tau in some form, and was proved by Johnston that if you let one of these slacks tend to infinity, S0, S1, and S2, in S1, S2, then you get this minus log E by pi S0 plus S1 sine of pi S0 by S0 plus S1. So our goal in this work is to obtain upper and lower bounds on this surface tension function. We would really like to find the surface tension function closed form exactly, which we are not able to do that. So we are going to try to find upper and lower bounds. So the way we'll go about this will be through random matrices. So the Gaussian unitary ensemble is the set of all is a measure on Hermitian matrices where the non-diagonals have are Gaussian, complex Gaussian with total variance 1. The diagonals are Gaussian, real Gaussians with variance 1, and it has this property that's conjugate transposes itself. Otherwise, they're all independent. Okay. And so now I just want to tell you some numerical values of that V. So I talked about V and lambda n. When lambda n corresponds to a semicircle law, which is what happens in Gaussian GUE matrices, then this has a specific value. So I'm talking about lambda n being this kind of value. I guess it is. It can be derived from the semicircle law. The semicircle law is sort of the limit of the histogram when the eigenvalues come from a GUE. But what we had, these surfaces are the cumulative sums of the eigenvalues. So there's some transformation that allows you to go from the semicircle to the curves that we care about, but I won't go into that. And this is the limiting value of V of lambda CL. Okay, and so it's got all this. And it can be shown, it's a calculation, that this is equal to 5 by 4. So it's from random matrix theory, you can do these calculations, and you get 5 by 4. Okay. So what we basically want to do is we want to get a handle on these surface tensions, which is something that is defined at a point in this giant hive. What we will be able to do, however, is to get the volumes of certain hive polytopes, huge hive polytopes, and then we'll use some convexity properties, etc., to get some bounds. So that is our goal. And so in order to basically to get at the hive polytope when lambda, mu, nu come from a semicircle law, we are going to look at some Gaussian integrals. And these Gaussian integrals will allow us to do some explicit computations, which will give us some values for the integral of the surface tension for the hives corresponding to semicircle laws. So these are GUE boundary conditions. Okay, so what this is saying is that if you take the same Vandermonde terms, take the hive polytope multiplied by a Gaussian, and you integrate this over the cone of all overall of all triples of n tuples such that the trace condition holds. Okay, then this integral, which is a Gaussian integral, has a closed form, namely it is equal to this. Okay, so why is this useful? Because right now we have no handle on this. This is saying that there's some smoothed out version of this whose closed form we know. So that's like a data point for us. It's like an integral of certain surface tension will turn out to be equal to this quantity. But I'll just indicate how this is proved first. So this is proved by using Cucurella-Zoubert's formula and together with some GUE stuff. So what is true of a GUE? You take two independent GUEs with variance A and B, variance A square and B square. When you add them, you get a GUE with variance A square plus B square. So because of this, And this is the transfer function of going from of observing nu when lambda and mu are the spectra. So because of this fact, this particular integral has a nice closed form. What? Because this is basically saying you take two GUEs, add them, examine the spectrum. Let's ignore this product term for the moment. What is it? We know it's a GUE with twice with the variance, which is the sum of the two. So this is basically just doing that. And this ends up having a closed form. And what is the closed form? It's simply a GUE. This is the distribution of getting the spectrum of the sum of two GUEs. Okay, so that GUE form is basically this, but because there was an extra e raised to minus nu square by c square in the term, you have to do some completing the square, and you find that this is equal to this. So this is how this term pops out actually. And this, of course, integrates to 1 because this is again another GUE measure. So you do another integration, you get this goes to 1, so you get this. So this is the argument for why that Gaussian integral is equal to this. So now there's another ingredient, which is that these V lambda n terms, they are actually, so more precisely V lambda n divided by V tau n. This is also the volume of a certain polytope called the Gelfand-Sutton polytope. And I'll tell you what that Gelfand-Sutton pattern is. The set of all such patterns forms the Gelfand-Sutton polytope. So what is a Gelfand-Sutton polytope with eigenvalues lambda n1, lambda n2 up to lambda nn? So here you write the lambda n1, lambda n2 up to lambda nn in decreasing order. Then you have a line here, write the numbers on these. You always have the inequality, this has to be greater or equal to this has to be greater or equal to this. Okay, so these are the interlacing inequalities you would have if you took any fixed Hermitian matrix, looked at its eigenvalues, took its successive principal minors, dropping the first row and first column repeatedly, and looking at the spectrum. So then if you did that, you would get the sequence of eigenvalues and they would satisfy these interlacing inequalities by Cauchy's interlacing law. But it's a remarkable fact that was shown by Baryshnikov that actually if you take a random Hermitian matrix with these eigenvalues and then you take these successive minors, then this resulting pattern that you get called a Gelfand-Sutton pattern is uniformly distributed in the polytope of all possible such patterns. Okay. So what we want to do is we want to use this Gaussian integral and get some mileage out of it. So what we'll try to do is we'll try to get bounds on the Hive polytope volumes using that Gaussian integral. So in order to do this, that Gaussian integral had some somewhat complicated form involving van der Waals and so on. But what I want to do is I want to define a triply augmented hive. Okay, so this is a triply augmented hive. So this is a hive. On its three sides, you have Gelfand-Sutton patterns. Okay, so I had in the previous page an example of a Gelfand-Sutton pattern. This is going to be a triply augmented hive. So it's got a hive in the center. It's got pasted to it Gelfand-Sutton patterns, which agree on the boundary. So the boundary has this lambda mu nu. So here also the Gelfand-Sutton pattern will have lambda mu nu correspondingly. So this object has the advantage that it gets rid of all the hive terms and the Gelfand-Sutton terms. Because if you look at the cone of all triply augmented hives and you look at a Gaussian measure on top of that, the integral of this Gaussian measure on this cone is precisely the integral of this f lambda mu with the right normalization. So the reason is that the volume of all hives with given boundary condition is the hive polytope, that was that Hn term. Then you have this GT lambda term here, which is V lambda by V tau. Then you have this V mu by V tau. You have V nu by V tau. So this is a way of taking all those terms and making them into the volumes of certain spaces instead. So instead of having a Gaussian, instead of having a complicated looking integral, we now have a simple Gaussian integral, but on a augmented space, a larger space. So the Gaussian measure is now on the space of triply augmented hives. The original Gauss way it was defined, it was on 3n-1 dimensions of spectra. No, because v lambda by v tau is equal to the volume of Gelfand-Setlin patterns with side length lambda, with the maximum side length lambda. So what is being done here is so this term, these three terms are being encapsulated by these three Gelfand-Setlin patterns. This term is being encapsulated by the hives. This term remains, but this is a plain Gaussian. So we are now looking at a Gaussian, this plain Gaussian integrated over a certain cone, but this is a 2n squared dimensional cone rather than a 3n-1 dimensional cone that we started off with. Okay. So now, because on the marginals of this on this side are simply GUEs, we know that the variance of the sides. So the variance of one side of this augmented random augmented hive that we get is precisely this. By variance, I mean you take the L2 norm squared and take the expectation. Okay, so what have we done? We have said that there's a certain Gaussian measure whose marginals on the three sides of this picture have known variances. Okay, and so what can we do with that? Well, it turns out that Gaussians maximize the differential entropy given the variance, this kind of variance constraints. Okay, so if I tell you, give me a measure on triply augmented hives such that the expected squared of the L2 norm squared of this side is so much, expected L2 norm square of this side is so much, expected L2 norm of this side is so much, then the thing that achieves that is this Gaussian on this cone. And this can be shown using KL divergence calculations. So what does this imply? It implies that, so this I'm restating this actually. So among all densities Q supported on this cone of triply augmented hives that satisfy these variance constraints, the unique probability distribution that maximizes the differential entropy is the restriction of this Gaussian to this cone of triply augmented hives. So in particular, what this means is that suppose I started with some other boundary conditions, lambda, mu, and nu, with the same variance. So sum of squares of entries being the same. I have to add a little bit of fuzz, otherwise the differential entropy goes to minus infinity, but I won't go into that. But if you do that and you take the augmented hives volumes, that will be less or equal to this, because this is the thing that maximizes entropy, differential entropy. Okay, so if you have any other lambda, mu, and nu satisfying these variance conditions, so this is square root of variance. When I write this is Euclidean norm, so it's just square root of L2 norm squared. These are deterministic boundary conditions, but you can use the same differential entropy based argument to this by adding a little bit of fuzz to this lambda, mu, nu, and making them densities rather than singular measures. This thing will be singular measure, and then you get this and then you get that the log volume of this augmented hive gadget is less or equal to this. So this is true for any lambda, mu, nu with these constraints. And secondly, it is maximized for semicircle law satisfying boundary conditions. Okay. So if you take the expected expected eigenvalues of a GOE matrix, which is essentially going to be very close to what's given by a semicircle law, then this is actually an equality. So it's a tight statement. It's for large n. I mean, there's a little o1 here. There is a little o1 here. So it's true in the limit as n tends to infinity. Yes. Yes. So this requires a statement of Fradalisi, which is actually very useful. So I'll mention it. So if you have Rm and you have a log concave measure, right? Then the mean and the mode can be different. So this is this is let's say the mode, and this is let's say the mean of the density, right? So you take expectation of x, that is equal to, that is the mean, but this mode is the point where the density is maximum. So what this result of Fradalisi says is that the value at the mean is greater or equal to e raised to minus m times the value at the mode. So while it can be less, it is not that much less. And the point is, in our setting, this m was actually some 3n minus 1 or something. And the whole space was n squared dimensional. So these things are all, you should think of these things as all being of the kind x of order n squared, x of theta n squared. So these are huge things. And this is a very low dimensional space in comparison. So this is what allows you to get this, basically. At the expectation, you don't lose much mass. And that is what tells you that at the expectation, you will get a good value. So now I want to talk a little bit about exactly sampling random augmented Hives. So we wanted to check certain facts about some candidate scaling limits of random Hives. We kind of guessed that they will be good, and they turned out to be kind of good, but they're not exactly right. But nonetheless, if you have a candidate guess for what is the shape of a random Hive and you want to disprove it, then one way of doing it is to sample the Hives randomly and check, does it look like that or not? So this is actually an algorithm for sampling random augmented Hives exactly. One caveat is that these augmented Hives are not triply augmented, they're singly augmented. So you should think of these as a Hive with one gel fan certain pattern pasted to one side, not three, not three. So this is the singly augmented Hive. So we want to sample these randomly using the Gaussian measure. So what is the process? The process is you first take the minor process, okay? So you start with, you pick a GUE measure, you take the eigenvalues of the GUE measure, drop one row and one column, get the eigenvalues of the resulting matrix, drop one row and one column, get eigenvalues of the resulting matrix, drop one row and one column, and repeat until you get a pattern. This is going to be, this is from a GUE, so this first row is not fixed, it's itself from some GUE measure. So this turns out to be a log concave measure on minor processes. This whole thing is a log concave measure on some cone. So what we're going to do is, we're going to take these two random minor processes and kind of transform the two of them into a augmented Hive. So I don't think I need triply augmented Hive anymore, so I'm going to erase this. So we're going to take these two gel fan certain patterns and produce an augmented Hive out of that. So first of all, you have a gel fan certain pattern, you have to first turn it into a Hive. How do we do that? There's some process of giving large gaps to the slopes here. So this you can think of as the x derivative of a Hive. But if somebody just gives you the x derivative of a Hive, it's not clear how to get a Hive out of it. So you add some extra data, basically the derivatives in these directions, discrete derivatives in these directions. So you do have to specify some discrete derivatives in these directions, and then everything gets specified once you do that. And the values of these discrete derivatives here have to have big enough gap that there will be no contradictions to the rhombus inequalities. So is this making sense? Or? No, we are not actually. I'm sorry. So what is being this picture is getting flipped, and this lambda 1, lambda 2, lambda 3 has gone here. Lambda 1, 3, lambda 2, 3, lambda 3, 3. It's only here that the big gaps are being put. So once you put, so the thing is, this and this are fixed already, right? Or something. Which two are fixed? No, sorry. This gap and this gap are fixed by the Gelfand-Sutton pattern, right? So now if I take, no, only the edge value. These are on the edges. These numbers are written on the edges.
Yes.
Yeah.
Yes, but that would mean that the point is 0, the first one is lambda 1 3 and lambda 1 2.
Yeah. Yeah.
And similarly, gamma 1,
yeah.
lambda 1, lambda.
Yeah.
But and and you're saying it like on the points on the falling edge, you put lambda 1 2 plus lambda 2 2.
Yeah. Yeah.
Plus lambda 3.
Yeah. So because these x derivatives are given, if I tell you what this value is, I know what the values here are. If I knew what this value is, I know what these are, but I don't know the value of this if I just fix the value of this. So I have to tell you the gap here. That's what I'm telling you. Telling you the gaps here. So there is some way of producing a hive like this. And then what is done is you construct a double hive like this using two of these hives inherited from Gelfand-Sutton patterns. Okay, so there's two of these hives, one with mu and one with nu. The terminology has changed a little, sorry. But this is basically two of those objects, two of those hives that were obtained from the minor process. Yeah. So yeah, so here, no, so this is obtained from eigenvalues, this is obtained from eigenvalues. This is obtained from large gaps. And this is all you have to fix. Once you fix it, it just sort of permeates everything like this.
So how are these large gaps? There should be something about like they just be much larger than.
Yes, they have to be much larger. So I skipped this thing here. But anything large enough works, yeah. So I think somewhere here there was this. Yeah. Lambda is said to have large gaps if the gap between the contiguous lambda I and lambda I plus 1 is greater than the maximum difference between lambda 1 and yeah. This is the condition. Okay, so once you have these two hives, you run something called the octahedron recurrence. So this is called a double hive. We've got two hives, one on top, one on the bottom. And you run something called the octahedron recurrence on a tetrahedron, where this is the top two panels, which are facing us, and the bottom two panels are below. Okay. So you run this octahedron recurrence and you get some values of the bottom two panels, and what you see on the bottom two panels is an augmented hive. Yeah, here, this is doctor. So yeah, so you should think of, so if you're looking at the tetrahedron, like this, then the octahedra have vertices. The top vertex of the octahedron is pointing to the top, pointing into us. Yeah.
What is the correspondence between the octahedron and the double?
So the double hives are what you see on the top two panels of the tetrahedron. This is now in the interior of the tetrahedron. This is the interior of the tetrahedron. So you're running this octahedron recurrence in the solid tetrahedron. And this is the octahedron recurrence. F plus E equal to the max of A plus C and B plus D. So you think of this top two panels having those double hives we constructed using Gelfand-Sutton pattern, minor process and all that. Then you run some process. No, you don't see the panels here. You see only in the previous picture. So these are the two panels, PQS and PSR. These are the two panels which have.
QS is the.
Yeah. Yeah, I'm sorry. That's the correspondence I may not have got right, but yeah, in this picture, QS is the middle. Yeah, so you're going this way. Yeah.
The octahedron is the octahedra inside the tetrahedron.
Yes.
They're tiling the tetrahedron.
Yes. So you do that, and when you look at the bottom two panels, what you find an augmented hive like this. And this is a measure preserving transformation from the top two panels to the bottom two panels. So if you started with random Gelfand-Septin patterns from Baryshnikov's result, what you get at the bottom is a honest random augmented hive with the right boundary conditions, because this process is measure preserving. And yeah, so this is kind of a miraculous fact due to Knudsen-Tau and Woodward. But this is so in particular, when you look at that middle side labeled gamma, this is precisely the spectrum of the sum of two matrices with spectra mu and nu, because that third side. So this you should examine this carefully. Here you have a hive polytope. Here you have V gamma, which is the volume of this Gelfand-Septin pattern, which is also the volume of the GT patterns here. So on the numerator, you have the volume of the augmented hive polytope. Okay, so the probability of observing gamma here is the probability is proportional to this thing, the volume of this augmented hive polytope. So why am I doing this? The reason I'm doing this is I want to generate random augmented hives and see what they look like. So this is what they look like. These augmented hives when you take two GUEs. So as you see, the smaller arches are roughly 1 by root 2 times the height of the larger arch, and this is because if you take two GUEs with variance 1, 1, when you add them, you get a variance of 2. So in order to produce this, we needed to use this algorithm. So one alternative for producing such a hive would have been to use Markov chain Monte Carlo on this log concave measure. And we, in fact, ran into some difficulties because they didn't seem to, give mix. So, but this is an exact sampling algorithm, actually. And so now I wanted to talk about what's a canonical hive I'll construct, which I'll try to compare with this hive. So what we'll do is we'll set one of the sides to 0. Then it turns out that there's a unique hive with that one side 0. And then we'll add 3 of them together in some proportions to get a hive. Okay, so you add 3 together, you get a hive. This seems like a reasonable heuristic to producing a hive. But so this is a reasonable heuristic, but it is not always exactly right limiting shape. And if you see here, the average estimate using sampling has height roughly 6,000. The heuristic again has height roughly 6,000, but sorry, this 4,000 or 4,000, 6,000. But the gap is roughly of a much smaller order, roughly 4%. Okay, so this gap is roughly 4% between that estimate and what we started off with. So now what has this got to surface tension? What to do with surface tension? So I'll go a little fast here. This is recall that surface tension was the volume of some polytopes. So what we got is we have this equality of involving this volumes of augmented hive polytopes in a closed form. And this translates into an integral of the surface tension over the hive. So what we have now is this is unknown surface tension. Hive is unknown. It's some surface, some surface that spans the right boundary conditions which we know. And we know the integral. So we know the integral over the Hessian of some unknown function. But if we assume that this unknown function is actually the function you get by putting together those canonical hives with 0 boundary conditions in some proportions, then you have a bunch of linear equations in effect, because you know the hive, which is not the right hive, but it seemed close, and you get all these linear equations. So can you solve them at least numerically? Okay. So we tried solving them numerically by discretizing, because there are infinitely many variables in this linear equation, so you have to discretize in some way. We discretized it and let's solve using some basically some constrained optimization type thing. So it was to you're solving linear equations under the constraint that sigma is convex, because you know that sigma is convex. So we added that constraint also, and in the process we got some candidate surface tension. Okay, so we solved a bunch of linear equations under the constraint that sigma is convex to find sigma, and we got this function. So why is this being written only over a triangle? This is a function over a triangle. So sigma has some symmetry properties, namely sigma of S by capital S can be expressed in terms of sigma of little s. Okay, so I don't know if I have that here. So I put that before this somewhere. So yeah, so sigma of S0 by S, S1 by S, S2 by S is equal to sigma of S0, S1, S2 plus log S. So you can, if you find sigma on a triangle subsection of R3 plus, you're good enough, you're fine. That's what is being done here. So this is what we see. So we got some nice shapes, and there are some tests we could run, and they seem to be reasonable. So first of all, there's a closed form that closely approximates this numerical value. So it's some function. And secondly, if you look at the boundary values, where you know the entropy because of Slack-Tanko-Tau and Johnston, then it seems to agree. So the boundary values are over here, and it does seem to be close to zero. This is a numerical function. Subtracting from that this. So say numerical thing minus this. And here you do seem to be getting something like zero. That's like a sanity check. And so I'll not recall this. So we wanted some, of course, some rigorous bounds as well. So what you can do is, like I discussed how if you take these hives with any boundary condition with the right variance, you get an upper bound using that Gaussian integral. So in particular, you can take, in this picture, you can take a hive which is completely quadratic. And when you apply this to a completely quadratic hive, you get an inequality involving the surface tension. You get that e raised to minus sigma is less or equal to this quantity. So you get a bound of this form. And then using the canonical hives, one can also get a bound, which is of the form e to the minus gamma, where gamma is the gap between the surface tension integral associated with the canonical hive and this minimum surface tension hive with these boundary conditions. So you get a lower bound as well. So note that this part was common. This part is value 3.5 or so. In the preceding thing, this part has value roughly 4.1. Okay, so that is the kind of gap between the upper and lower bound. If you ignore this, which we hope is small, because when we did that sampling, the gap between the two, the random samples and the canonical hive seemed rather close. So I think I want to stop here. So are there any questions? I'll like to show you some pictures later, but just if there are any questions, I'll stop here. Okay, so I'll just tell you one fact that I think is interesting and show you some pictures. So this way of producing the hives using the octahedron recurrence, it has a closed form also. So this is some iterative procedure of getting the bottom two hives using the top hive, but it's got a closed form using Spear's formula. So what is this Spear's formula? It is in terms of maximum weight matchings of the underlying double hive on the top two panels. So here you have this top two panels, you have an excavation hexagon. And in this excavation hexagon, you have to look for maximum weight matchings where the weights are somehow related to the interlacing gaps of those minor processes on the top two panels. So when you take the maximum weight matching of this graph, right? So there are some specific weights that you have to get. It's not exactly weight, it's you basically take the polytope of all matchings and you optimize a certain linear function, which is written here. I think I don't have time to go into great detail, but it is essentially a maximum weight matching, and you look at the maximum weight of that maximum weight matching, that is exactly the same as the value of the hive on the bottom panel. So it's like a closed form. So you don't have to do the recurrence necessarily to get the value below. You can take the top two panels and take the maximum weight matching of some excavation hexagon and look at the weight of that, and that gives you the weight of the value of the bottom augmented hive. So what we're doing here is we are taking these edges and turning them into lozenges by rhombi. And the reason we're doing this is so that we can look at it as a surface. So as you see, so I'll take 2 more minutes. Okay, so you get a surface. This looks like a surface. And you can do this for much larger things also by solving finding the maximum weight matching and plotting it like this. And so these are all AB, AB, AB type hexagons. So this thing is equal to this thing is equal to this thing. This thing is also equal to this thing equal to this thing, and it has this nice shape. And they look like surfaces also. So you can analyze these random matchings using some function theory by associating with them a function. This is what is done in the Dimer's literature. So I'll just briefly tell you some related research on Gelfand. So this I went through. This Johnston-Prochnow recently proved a large deviation principle for random Gelfand patterns with the same surface tension. And on hives, we had some work with Sheffield and Tao for the variance of a random augmented hive. And building on that was shown in recent work that they also converge in probability to a single continuum hive as n tends to infinity. And here are some open problems. So is there a closed form analytic expression for the surface tension of a hive, which is what we were trying to get to using these inequalities? And is there an asymptotic shape for the tiling height functions, those pictures that I showed you later? And is there an analogous set of results for integer valued hives giving asymptotics and bounds for Littlewood Richardson coefficients? So not only is the random point in the whole Lebesgue measure equipped polytope of interest, even the lattice points in these polytopes are of interest. They occur in representation theory, and people would like to know what do these random integer valued function hives look like. So with that, I'll stop. Thank you. Thanks.
Questions?
Yeah. Yeah. Yeah, if it were integer valued, then yeah. Yeah.
More questions? So if not, then let's thank Hari again.
Thanks, sir.